Hello, I'm Richard Pelphrey, and today I'm presenting work done by myself and my advisor titled A Multi-Resolution Analysis of Temporal Logic. Our work is motivated by runtime verification and distributed systems. In runtime verification, we ask the question, does the signal satisfy the specification? In a distributed system, there is some external node or sensor, such as this buoy, collecting environmental data, which it then transmits to some central monitor, such as this tower. And the monitor asks the question, does the signal meet the specification? In reality, the buoy would first decompose the signal into a low resolution approximation and a series of details. It first sends the low resolution approximation x minus 2, and then it sends the details d minus 2, and the tower adds the approximation to the details to get to the next level approximation x minus 1. And then the buoy sends d minus 1, and the tower adds x minus 1 and d minus 1 together to get back to the original signal x. In this manner, we fully reconstruct the signal. This decomposition is called a multi-resolution analysis, and this multi-resolution structure is inherent to signals. Given a signal, we can decompose it into a low resolution approximation of the signal, x minus 1, and the details, d minus 1. And then we can further decompose x minus 1 into x minus 2 and d minus 2, such that when the approximation and the details are added together, we get back the full signal or the original signal. And this can continue to be iterated down to x minus 3, x minus 4, and so on. This idea is used all over the place in signal processing, from our phones to distributed systems to Zoom, which we are on right now. So then we need to talk about why it's used so often. So let's sort of loosely use this example of Zoom that we're on right now. If you, the audience, drop bandwidth while watching this, the result of that is that maybe you won't receive some of the details. So maybe instead of receiving x minus 2, d minus 2, and d minus 1, all you receive is x minus 2 and d minus 2. So you get a low resolution approximation of my presentation. The video might be might be really low quality, and my voice might be a little bit weird. You might lose some of the details. But despite those two things, you still have what is hopefully a reasonable approximation of my presentation. You still have this x minus 1, which is pretty close to x. So you get the gist of the presentation, maybe with poor resolution and funny voice sounds, but the gist. So now what happens if in runtime verification, we only get one of these approximations? If the receiver only receives a low resolution approximation, is it then able to make a determination about whether the specification is satisfied? That is what we answer here. So runtime verification does not currently utilize multi-resolution analysis. Up until now, we need the fully reconstructed signal in order to perform any sort of monitoring. Answering our question, or this low resolution monitoring, requires creating a multi-resolution analysis of the temporal logic itself. In other words, we need to monitor a low resolution signal against a low resolution formula. And this multi-resolution analysis of the temporal logic is possible. We can create a low resolution formula for each approximation signal and detail signal for each level of decomposition. Discrete-time signal temporal logic provides these unambiguous formal specifications needed for runtime verification. I've written out the full syntax here, but for this presentation, we only need to worry about the proposition, which is the most basic element of a formula and the most basic statement you can make about a signal, something like x is greater than 0.5. We also need the globally operator, which applies the proposition to an interval, in this case, 5 to 7, and requires that over each time in the interval, the proposition holds true. Our signal model is periodic discrete time signals. This is the simplest setting under which a wavelet decomposition is possible, and the wavelet decomposition is actually used to achieve this multi-resolution analysis. To get the approximation and details, we first create what is called a wavelet basis. When we project onto one part of this basis, we get the approximation, and when we project onto another part, we get the details. This again has the property that if you add the approximation to the details, you get back the original signal. There are a variety of wavelets. Some examples are the Haar, Shannon, Debauche's wavelets, but there are others. And again, to reiterate, the decomposition or multi-resolution analysis results in a low-level approximation, such as x minus 2, and different levels of details, d minus 2 and d minus 1. Such that when you add x minus 2 to d minus 2, you get back to x minus 1, which is becoming a better approximation of our original signal. And if you add x minus 1 to d minus 1, you get back to the signal x. So as you go from left to right, you are reconstructing the signal. And this brings us to our first theorem, the multi-resolution analysis of discrete time signal temporal logic. So given a signal with a multi-resolution analysis and a DTSTL formula phi, then there exists an approximation formula phi minus 1 and a details formula delta minus 1, such that x satisfies phi only if x minus 1 satisfies phi minus 1 and d minus 1 satisfies delta minus 1. And once again, these formulas follow a similar structure to the original signal. There is a low resolution formula for both the details and the approximation at each level of decomposition. Now, the question that you might be asking is, can we say that if x minus 1 satisfies phi minus 1, does that mean that x satisfies phi? And the answer to this is not necessarily. The approximation is a projection, so we've lost information. We do not have access to enough information about the signal to determine satisfaction of the original signal. We can only really find a violation. We do have an alternative characterization that results in an if and only if statement. And that is a set of mixed integer constraints, but we won't go into it here due to time limitations. However, this early violation detection is one potential application of this. So in early violation detection, the receiver would know the full multi-resolution analysis of phi, and we would start by receiving the lowest level approximation. So the monitor receives that lowest level approximation and checks whether the approximation satisfies phi minus j. If not, we would declare a violation and stop here. If it's satisfied, we would continue. And then the monitor would receive the next level or the details and check whether the details satisfy delta minus j. If not, we declare a violation and stop here. If it's satisfied, we compute the next level approximation by adding the current approximation to the current details, and we continue. We increment j, and if we find that we are back to the original signal, we check that the original signal satisfies the original formula. If we're not yet back to the original signal, we come back here to step 2 and repeat the process until either we find a violation or we get back to the original signal. Now we need to begin to look at these low resolution formulas in slightly more detail, starting from the most basic element of the low resolution formula, which we are calling an extended proposition. We call it this because an atomic proposition acting on xn induces a constraint not only on that same position of the approximation, but also potentially on each and every position of the approximation. And this is because each element of the approximation is in effect a weighted sum of the original signal. To find these, we also assume some state bounds, typically something like the signal is between negative a to a. And this gives us enough now to go through a quick little example here. So if we define the proposition x is greater than 0.5 and the state bound negative 1 to 1, then the resulting extended proposition using the Haar wavelet is here for the approximation formula and here for the details formula. If we find that at any point the approximation is outside the bounds of these black lines, then we have a violation of the extended proposition and thus the original proposition, similar for the details here. So given that we have calculated and found the extended proposition, what does the full formula look like? Well, nicely, it does have the same structure as the original formula, just with extended propositions instead of your original proposition. So for an example, you have a formula globally over an interval P. Then the decomposed formulas are globally over the interval P minus 1 for the approximation, and globally over the same interval Q minus 1 for the details, which is pretty nice, really. Now let's look at a simple example for monitoring. So let's look at the case of globally over the interval 5 to 13, x is greater than 0.5. Our signal x is this Gaussian right here, and we can see immediately that this signal does not satisfy the formula. You have 3 points of x that are satisfying the proposition, but the rest do not. And part of these rest include positions in this interval. So for example, position 5 does not satisfy the proposition. So now we decompose x and find the approximation, x minus 1 right here, and we construct the extended proposition. And now we can monitor. So here we're checking position 11. So we've checked over this interval 5 through 10, and we get to position 11 and we see this. We see a violation in position 12 of the approximation. And what this means then is that position 11 of the original signal does not satisfy the proposition, so our overall formula is not satisfied. So we found a violation in the low resolution space, meaning that back in the full signal space, we have a violation. We do not need to continue monitoring. We do not need to reconstruct x fully and monitor that. We know x does not satisfy phi. So we detected a violation, but I do want to mention one more thing. It does potentially matter which wavelet we choose. So here we're comparing the extended proposition for the Haar wavelet to so the Haar wavelet has much tighter bounds than the Debauche's wavelet. That previous example, you would not have caught a violation with the Debauche's wavelet. That's not to say that you can't catch violations. It's just going to be more difficult in general with the Debauche's than with the Haar. So with the Haar wavelet, you're probably more likely to catch a violation. But that a full characterization of that would be future work. So unfortunately, not all signals are periodic in discrete time. So in the future, we'd want to extend this into L squared Z, which is infinite, not necessarily periodic discrete time signals, and to continuous time. We also want to remove an over approximation that I didn't talk about, but does exist currently while we're creating the extended propositions. Removing this over approximation would allow us to hopefully detect the violations more frequently when they are there. And we're working on these two things right now. But we'd also like to maybe do an investigation into the benefits and drawbacks of different wavelets at some point in the future. Thank you.